Hello and welcome to tutorial number 10 of Introduction to Deep Learning. Today we'll review exercise 9 that you submitted this week and look at some solutions. And then we will introduce semantic segmentation that you will be working on in the next week. And finally talk about the survey that you have filled. So I would like to start with looking at the leaderboard from this semester and compare it to the one from last semester. So the one from this semester is down here, and you see that you guys slightly beat the students from last semester, which is cool. But overall, the numbers are pretty much the same. More interesting is to look at the table from last semester. So we see here that the best student got 942. And that is because in that semester, we were not using transfer learning for this exercise. But it's still interesting to dive into this solution and look what this student did there and see what we can learn from his solution and figure out some good and bad practices. So when we look at the code, it looks quite simple. We can see 4 convolutional layers and parametric ReLUs, which are like leaky ReLUs, just learnable parameters for the slope of the negative values, and max pools in between to downsample the spatial dimensions. And these all convolutions are considered the feature extraction, and then we have a flattening of the feature maps, and then the linear layers here to get the final classification or the values we want to regress. So first, looking at it, we see that the student tried to use dropout but left it out in the end. One idea why they left it out could be that the model is not too big to start with, and maybe with the dropout it was lacking capacity. Furthermore, the student uses max pools here to downsample the spatial dimensions, but this can also be done using stride 2s in the convolutions. Here in the convolutions, the student uses a stride of 1 with 3x3 kernels, and seems like the padding here is a bit random. And for the last convolutional layer, the student chose a 2x2 kernel, and then it goes into the regression or classification branch here. What's nice is if you use this torch summary, it gives you a nice summary of your model. And not only does it write all the layers that you have here, but if you input a shape that you start with, for example, an image of 96 by 96, then it already computes the output shapes of all the operations you're doing. So you can see after the first convolution, it actually increases to 98 by 98 and 32 channels, and it continues and goes down to 32 and then again up to 34 because of the paddings. This is a bit not standard. And you also get here on the right the number of parameters, of learnable parameters that each of these layers have. What's interesting here is to see that for the last convolution, you end up with an output of 9 by 9 in the spatial dimensions and 128 channels. And that is when we do the flattening. And notice that when you do the flattening from a 9 by 9 and 128 channels, you get this many neurons that you have to put through a linear layer. And that's quite a lot. And indeed, you see that this linear layer, the first linear layer that goes from 10,000 neurons all the way down to 256, has a lot of parameters, and most of the capacity and the parameters of the network are concentrated here. Because here altogether we have something like 80,000, but here we have 2.6 million. So it's a little bit unbalanced. And normally you would either go down slower, but what's more common is to try to have less less neurons in this first activation, that means you either don't have 9 by 9, but something smaller, or maybe less channels. All right, so how can we make a smaller linear layer and have less parameters there? So one way is, instead of having 9 by 9, you can go down all the way to 1 by 1 even in the spatial dimensions and have, for example, 128 channels. So one way to do this would be to take a convolutional layer with a 9 by 9 kernel. A more standard way to do it would be to do maybe a few convolutions, not one 9 by 9 one. But this is one way that it could work. Another option is using global average pooling. This is kind of like max pooling, but you do it on the entire spatial dimensions of the input. So if you have a 9 by 9 input, you look at all the 9 by 9 values and you choose the maximum there. And you do it for every activation filter you have, and this way you can treat them as kind of probability maps and put that into a softmax layer. This is done in some ImageNet classifiers. You can read more online about global average poolings. The one disadvantage when you have this is when you do these max pools, but especially the global ones, you kind of lose the spatial contexts. So in our case, what we want to do is regress the positions of the facial key points, and if somewhere in the network we're losing this spatial relations of where in the image each feature came from by doing such a global average pooling, maybe it's not the best thing for this task. And maybe it's more suitable for classification, for example. And one more thing we could do is just stay with the 9 by 9 spatial size and just lose some of the channels. So maybe we don't need 128 channels, but we can do with less. And one great way to get rid of too many channels is 1 by 1 convolutions, because these convolutions only act through on the depth of the tensor that you have, and they don't change the spatial dimension, and you can just use these convolutions to reduce the number of channels you have, for example, from 128 to 16. So if we do that here, then we see now that we go here from 128 channels and 9 by 9, we go down to 16 channels and 9 by 9 after this 1 by 1 convolution. And we have much less parameters here. And now when you flatten this and put it into linear layers, then you just have 1,296 neurons and not 10,000. And in turn, you have much fewer parameters and a smaller network. And hopefully this layer would be less prone to overfitting. And after this, what you could do is, of course, try to go deeper. And maybe if you go deeper, you might start having issues with gradients exploding or zeroing out. And at this point, you might want to consider residual connections. And as for the hyperparameters this student was using, so this was the learning rate and this was the batch size, and the rest stayed untouched. And probably any of the activation functions would work, and maybe it's not too important that the batch size was 512. This is what worked for him, but I'm sure many other combinations would work as well. So that's all for the case study. And now we can move on to semantic segmentation, which is what you will be working on this week. So in semantic segmentation, we get an image as input, and we don't want to just put one label on the entire image, but we want to get a label per pixel, as you see here in the image down. So formally, you have an input, which is an RGB image, so 3 channels and width and height, and the output should be something with the same width and height, but now the number of channels will change, and in this example it will be 23 because you have 23 classes in your data set, and these are the classes that you want to predict for every pixel. And these data sets for semantic segmentation typically look something like this. The images are not always completely labeled, so that means you have pixels here, like the black pixels you see around the sheep, or in this image, unfortunately, most of the image is just unlabeled. So black here stands for a void class, and basically this can be ignored because the person who labeled it maybe did not have this label in their dataset or bank of labels that they can use. So these are not important, and we will just be taking loss values on the pixels that you have a correct label for them. So you want to ignore this black one also in your computations. So this will require a little bit of tweaking in the code to account for that. And we provide you with this piece of code here. And you can see that for each pixel, we will be using the multi-class cross-entropy loss. But we also add this ignore index parameter where if the void class has index -1, you just provide this here, and then this knows that every pixel where the ground truth label is -1 should not be considered for the computation of your loss value. Similarly, we also have this problem when we compute the accuracy metric. So we want to mask the image only where we know the labels, and that's how we compute the accuracy. All right, so as I said earlier, we have an input that's usually RGB, so you would have the batch size, usually 3 here for the 3 RGB channels, and the output will have the same spatial dimension, and here you will just have the number of classes. And we want to put it through a neural network that maintains the spatial dimensionality and yet is able to compute features along the spatial dimensions here, but at different resolutions. Because sometimes important features are small in the image, and sometimes you need more global context to realize what's going on and how to label this pixel. So the naive solution would be something like just a few convolutional layers that preserve the spatial dimensions, and you do a few of these, and then you end up with a tensor that has the same width and height and just as many channels as you want for the output. And there is a problem with this because although it's not expensive from a memory point of view to have convolutional filters, you do have to remember that when you're training this network for the backpropagation, you save both the input and the output of every operation, and that kind of blows up, and you will soon run into memory issues when training. And that is why it is a popular thing to do is very soon you start going down in the spatial dimension and have more filters. Another issue that we get if we just do that is what we call receptive field. So the problem is that by doing this, you will not get features at different spatial dimensions. So what I mean is this. So if the definition of receptive field is for every pixel in an output of the layer or in that output of the network, how many pixels from the input affected its computation. So if we take as an example 2 5x5 convolutional layers like we have here, then after 2 of these convolutional layers with 5x5 kernels, each pixel in the output has been affected by a square of 9 by 9 pixels. And that is what we call the receptive field of a pixel in the output. So if we keep this in mind, one great way to increase the receptive field of your network is by using strided convolutions or pooling layers to reduce the spatial dimension, and this way each pixel here is affected by many pixels in the input. And if you have the same architecture in mind as the student in the case study, where we have 2D convolutions and max pooling, taking us down all the way to a 9x9 image in the end with many channels, in the end, to get an output that has the same spatial dimension as the input, you can just take this 9x9 tensor that you get here and just use bilinear or nearest neighbor upsampling and bring it up to the same spatial dimension of the input. And this is how you can do your classification for every pixel. The problem is you get a very low resolution output this way because it's just coming from a 9x9 and it has been upsampled. Of course, you can later do maybe more convolutions after you upsample. This is a naive solution, but it will already work better than the previously shown naive solution, and you won't have that problem with the memory exploding because you're working with very big tensors in the first naive solution. So a better solution is to use something similar to the autoencoders that you've already seen, but this time with convolutions, not with fully connected layers or linear layers. And the idea here is to take the input, which would be an RGB image, and slowly with convolutions reduce the size, the spatial dimension, and increase the number of filters. And you do exactly the inverse of this when you start upsampling and you want to get to the same size as the input image. So you're creating this kind of bottleneck here, this latent representation of the image, where it is forced to kind of include the most important information about the image. And what's nice is that every operation here that you do in the downsampling part can pretty much be inversed. You can do the inverse operations in the sense of dimensionality to what you do here. So if you do pooling here in this part, then you can do upsampling in this part. And for strided convolutions, then you have those transposed convolutions. We won't go too much into them, but yeah, you can basically get back to the same size that you had here. And it's still all learnable filters, which is a great advantage that transposed convolution has over just upsampling. So what are exactly these transposed convolutions? It's a way to take an input and get an output that is larger in its spatial dimension, but similar to convolution. So essentially, we take this input tensor and we think of it as a larger tensor than what it actually is. So it goes through these transformations here, and then you just take your kernel and slide it along this, resulting in a larger output. The takeaway message here is that if you take a normal convolution layer, then you have this formula that we've already seen to compute the output dimension given the kernel size and the padding and the stride and the input size. And these transposed convolutions pretty much inverted. So we get this formula here, which could be useful for you to figure out which padding or kernel sizes you need to get the outputs that you want from your input sizes, which of course will change according to what you do in your network and how you downsample the input. And you can see more information about transposed convolutions in the link right here. Are transposed convolutions always better? So not always. Of course, the big advantage of transposed convolutions is that it's a learnable way to go up in dimensionality, as opposed to just taking a bilinear or nearest neighbor upsampling. And the reason why it's not always better is it's more related to image generation tasks rather than semantic segmentation. But when you're using these transposed convolutions to generate images, you have these overlapping patterns sometimes, which cause checkerboard artifacts on the images that you're generating, which don't look too nice, and it hurts the photorealism of your outputs. But as I said, this is more of a problem when you're trying to generate photorealistic images. And this just comes from the way these transposed convolutions are built. And you can use the link right here to see an interactive demo of how you changing the parameters of the transposed convolutions can cause these different patterns on the final result. So what you can do to avoid these, if you ever get these, just first do upsampling. The normal thing to do is bilinear upsampling, and then you can just do a convolution layer that preserves the dimension. So this way you still upsample your spatial dimension, but you still have something learnable in the process with this convolution. All right, so some tips for this exercise, how to compete and get results quickly. So the first thing that will save you a lot of time and get you a lot of accuracy is to use transfer learning. Our data set is not so big, and you have models out there that were trained on ImageNet that have seen millions of photos and are fine-tuned with hyperparameters, and it's a shame not to use them. So the old school approach would be to take some network that was trained on ImageNet and use the encoder and freeze it, and then set up your own decoder that learns to output the correct per pixel classes, and you only train this decoder. As for which networks you can use for the encoder, so anything that does image classification on ImageNet would be suitable. So if you go to older networks, you have AlexNet, which is quite simple in its structure, but a bit old. But if you want to also save computation and get state-of-the-art result, you can use MobileNets or MobileNet v2, which are quite lean and give really good results. And just throw away the branch that does the classification and use the network as some feature extractor and just go back up to the same spatial dimension from there. That's a pretty solid way to go. The even lazier way to go, which is take a fully pre-trained network that does image segmentation and just maybe add a layer to get the correct number of classes and fine-tune that layer to get the segmentations that are correct for our data set. This should work too, and might even be quicker, and will definitely help you get over the threshold pretty quickly. You might also want to consider using unit architectures. So these skip connections are quite helpful. I mean, some of the pre-trained networks already use them, but if you're implementing something yourself, then consider using these too. All right, so that was all for the material for the tutorial today. I just wanted to mention the teaching survey. So first of all, thank you to 89 students who took their time to fill in the survey. We know it's quite long and tedious, but it is very helpful for us. So thank you again for doing this. We wanted to discuss some of the comments that we read there that we thought were important. So I was surprised to see that many students said that there's no way to interact with the course staff, but there is, of course, which are the office hours. So if you're still not aware, then yeah, we have office hours basically twice a day, and you can contact the tutors, or if you need anything specific from me or Manuel, feel free to let us know that too. So there were some comments about Piazza versus Moodle. So there were 2 students out of the 89 who mentioned that they don't like Piazza, and we should use Moodle next semester. But I think there were almost like 10 comments that were in favor of Piazza and said that it's better than Moodle. So I think we will continue using Piazza for next semester. One comment said that without Piazza, some of the exercise contents are considerably harder to solve. I tend to agree with that actually, but I mean, I think Piazza is a really important part of our lecture, and it's just impossible to cover all the little issues that might arise in the notebooks, not only technical issues, but even some understanding of what should be done. It's just hard to cover all of that in the tutorial, and that's why it's so important to scroll some questions on Piazza when you start solving the exercises. And also, this is a tip for the exam. Sometimes there are questions about the material that are really good questions and even maybe make good exam questions. And it's important to see what people were asking there and the answers that they were getting. Next, this is quite a long comment, but the essence of it is that they say that it's not so good that you're not able to submit exercises after the deadline has passed, not in the sense of getting the bonus, but just being able to check your solution or still continue working on it. Or maybe if you even couldn't submit the exercise for whatever reason, but you do want to do it later, or maybe as preparation for the exam. And currently our submission system does not allow that. So actually, we think this is a really good comment, and thank you for suggesting this. But now we changed the submission system, so we have these dummy exercises here, and you're able to submit your models to these dummy exercises here, and these don't count for the bonus, and they open as soon as the corresponding actual submission ends. And here you can submit new solutions to the same exercise and at least get the output from the submission system, be it error or your score. All right, so please watch the next lecture on Monday and submit the exercise on Wednesday as usual. And next tutorial, we will present exercise 11, where you will be doing some NLP. Thanks, and see you next week.